Hi, my name is Jaejun Lee. I'm a master's student of School of Computing at KAIST. I'm a member of the Big Data Intelligence Lab led by Professor Joyce Jiyoung Whang. I'll present our paper, Semantic Grasping via a Knowledge Graph of Robotic Manipulation, a graph representation learning approach, which is a co-work with Kwak, Professor Joyce Jiyoung Whang, and Professor Sungho. Semantic grasping refers to task-dependent robotic grasps that are functionally suitable for specific object manipulation tasks. For example, when a robot lifts a glow stick, it is preferred to grasp the body of it. However, if our target task is to open the lid of the glow stick, a robot should grasp the lid instead of the body. Like this, a robot should grasp different components of an object depending on the tasks. In addition to the grasping regions, we can also consider gripper types and grasping forces for appropriate robotic manipulation. For example, to lift a strawberry, a robot should use a soft gripper. On the other hand, to squeeze the strawberry, a robot should use a rigid parallel gel gripper with a strong force. We propose semantic grasping that considers three factors: which component a robot should grasp, which gripper a robot should use, and how strongly a robot should grasp the target object. To achieve this goal, we create a new knowledge graph called roboKG, which represents human knowledge about desirable robotic manipulation for various tasks on various objects. By computing the embedding vectors of the entities and relations in roboKG using knowledge graph embedding methods, we predict the appropriate robotic manipulation factors and use these factors to operate a real robot. Our method consists of three parts. First, the recognition module detects what the object is, what components the object has, and what material the object is made of. For example, an object detection method recognizes this object as a bottle, and a component detection method detects three different components of it: body, handle, and lid. And a material detection method recognizes that this bottle is made of glass. Given the object and a target task, we predict where to grasp, which gripper to use, and how strongly to grasp based on knowledge graph embedding of roboKG. Last, a real robot is operated according to the predicted grasping factors. We create a new knowledge graph called roboKG to represent desirable robotic manipulation. We define 10 different entity types, 10 different relations, and 10 different triplet types in roboKG to represent object-related information, task-related information, and manipulation-related information. To represent an object, we consider what the object is, what material the object is made of, and what components the object has. For example, these triplets represent bottle 4 is a glass bottle with a lid. To represent a task, we consider each task categories. For example, open bottle is a subcategory of open, and open bottle 4 is a subcategory of open bottle. There are three special relations that are directly related to manipulation tasks: which gripper, which force, and which component. For example, these triplets represent how to open bottle 4. Grasp the lid strongly with the soft gripper. In the training set, we include this kind of triplet to represent appropriate grasping factors. At testing time, we predict which component a robot should grasp, which gripper to use, and how strongly to grasp. For example, we predict these factors for the task open jar 3 in this figure. A knowledge graph embedding method learns embedding vectors of the entities and relations by reflecting the structure of a given knowledge graph. By learning the embedding vectors of the entities and relations of roboKG, we can predict the grasping factors for the tasks and objects which were not explicitly provided in the training set. We consider 7 different robotic manipulation tasks: open, floor, rotate, lift, push, squeeze, and grasp. Let me show a short demo for a task 4. When a robot tilts the object 30 degrees after lifting it, we consider it as a successful trial. In this example, a robot used a rigid parallel gel gripper. Let me show another task, grasp. When a robot grasps the designated component of the object without changing the shape, we consider it as a successful trial. In this example, a robot uses a soft gripper. In the experiments, we first measure the accuracy of knowledge graph embedding methods. Given a specific object and a specific task, We test how accurately a knowledge graph embedding method can predict a suitable gripper type, grasping force, and grasping component. We used three different knowledge graph embedding methods: Hake, Burp, and Cone-E. We see that the knowledge graph embedding methods significantly outperform the baseline method, and Hake shows the best performance. Next, we operate a real robot based on predictions made by a knowledge graph embedding method. The three knowledge graph embedding methods outperform the two baseline methods, rule-based model and the centroid-based grasping. For the rule-based model, we specify the following rules. For the centroid-based grasping, we fix the gripper type to be a rigid parallel jaw and the grasping force to be medium. Last, we test an end-to-end setting where the objects, components, and materials are automatically identified by the recognition module. Among 43 test instances, the robot succeeded in 34 test instances, achieving the accuracy of around 80%. In summary, we defined roboKG, a knowledge graph representing the properties of objects, the relationships between tests, and the appropriate practice of robotic manipulation. By applying knowledge graph embedding methods, we properly generate semantic representations of the entities and relations in roboKG. And this allows us to make predictions on a gripper type, a grasping component, and a grasping force for semantic grasping. Based on the predictions, a real robot succeeds in accomplishing various tasks on diverse household objects. Thanks for listening. If you have any questions, please let us know. Thank you.